So, welcome to our introduction on good practices in HPC. Today, we are going to talk about why following these good practices in high-performance computing resources such as ours at HCC benefits not only you, but others using our resources, how to use monitoring tools and methods to evaluate your job resource requests. So those SBatch parameters that we talked about at the end of yesterday. Describing best practices and good practices for storing files on a shared environment and keeping your files safe, and examine support resources and methods to get more effective support. So why is it important to follow good practices in HPC, and how does it benefit you as a researcher? To provide some context on this, for those who have not been with us for the past handful of sessions, is HPC resources like Crane and Swan offered at HCC are shared finite resources used by many students, staff, faculty, and collaborative researchers, where at HCC, this can mean upwards of 300 plus researchers using the same resource at the exact same time. In comparison, you probably only use your desktop maybe with one other person on and off, maybe a few other people, or a workstation in your lab with a handful of people on and off, while Crane and Swan are actively used by many researchers all at the same time. And high performance computing itself is basically just taking a whole bunch of computers and aggregating their performance into one larger unit to solve problems of various sizes in many different fields. As we've also talked about for the past few sessions, there are four main components of a compute cluster. Excuse me. There is the login node, which is the system that we log into when we SSH. Similarly, kind of off on the side now is the Open On Demand portal that Natasha talked about just before the session. There's a management computer which runs the scheduler or the storm scheduler for the clusters, as well as stores the data about all the jobs that are running. There's the worker nodes, which actually process all of the jobs and computations for your workflows and the workflows of others. And then there's multiple, in fact, storage arrays for these systems, home, work, and common, that basically house all of your files. And there we go. And so the first thing we're going to look at is monitoring your jobs and optimizing your job requests. We're not looking at perfect 100%, you know exactly what your job needs, but more in terms of get in the rough ballpark in terms of optimization. And so to provide some extra context, to schedule our jobs and to help manage everything, we use the simple Linux utility for resource management, or Slurm, which is a open source scalable cluster management and job scheduling system that is used on the large majority of top 500 supercomputers, including Crane and Swan. It essentially assigns jobs and starts them up on the worker nodes from the management node based on available resources and your user priority. And your user priority is adjusted dynamically as you use the clusters more and more or less and less, where you, as a researcher, provide tasks for the scheduler to run out to the worker nodes. You submit those using the SBatch command that we learned about yesterday. That sends it off into basically a long line of jobs where, when based off of resources in your priority, at some point in time, it will execute your job to give you those results back and contribute to your research. This is done through an algorithm known as fair share, where the job priority that you have is based off of multiple factors, including how long your job itself has been waiting, by how much CPU, memory, GPUs, and time have been requested by your group, and if you've had any quality of service adjustments like a acknowledgement credit, where you can basically say you've used HCC and acknowledge it in a publication, you can get a little bit of boost of priority there. And this fair share value is essentially a 0 to 1 value of basically how much you've used the cluster or your general utilization of it, where 0.5 is the average utilization of everyone on Crane or Swan. And as you use either resource more and more, your fair share value goes down closer to 0, which is a reduced priority. While if you have not really used cluster at all, your priority is going to be, or your fair share is going to be near 1. And so typically a lot of newer users, especially if you just got your account or you just got your group, your fair share priority is going to be fairly close to 1, as it's technically underutilizing the cluster. While some of our top 25 users, their fair share priority is probably going to be fairly close to 0. And this allows newer users or newer groups to be able to run stuff on the cluster without the cluster being entirely used up by, say, 5 different people. So it's a way to help kind of balance resources out in a finite shared pool. Kind of a fun way I like looking at it is, actually, let me throw a question out to everyone in the room. So give me a green check mark in Zoom if you've ever had to go and schedule a conference room on campus or schedule a classroom. And give me a red X if you have not had to do that. Okay, looks like 3 green check marks. I'm gonna guess probably maybe only for a handful of people as well, maybe 5 at most commonly, or maybe even more. So the way jobs are scheduled is not too dissimilar from trying to find a conference room or classroom on campus, where you have how many people you're trying to find a room for, the amount of time for it, any special features of the conference room, such as allowing you to technically have food in it or having presentation functions. And this is similar to where we have CPUs, memory, special features on our compute resources, and the time, to where it's very easy to find a small room here on campus for, say, an hour. You can easily find a room enough for 4 people, say in Love Library or at the Union, or even in the many academic buildings here on campus without too much difficulty. Though if you tried to find a classroom to hold 200 students for 3 hours just on a whim, that's going to take a lot of time and effort on your part to try and get that classroom, especially for an event, and even more so to try and find one to say that allows food. Since, say, the College of Business here at the University of Nebraska-Lincoln, they don't typically like food in their classrooms, which makes finding a 200-person room much harder. And if you only needed a room for 5 people, but you try and get the 200-person classroom, that's a underutilization of university rooms or resources. And a similar concept happens on high performance resources, where large memory requests or large resource requests can happen. But if you're not using all of those, then it's an underutilization of the requests that other people who could be needing those resources could then use. So it's a kind of a very similar idea. And it's kind of a relatable one, especially for a lot of instructors or grad students working on collaborative projects. There we go. And Amazon, actually, in fact, they have their own batch compute service as well. Costs a lot, but if you give them a credit card, then they'll happily let you use it. Where on their documentation, they put their scheduler in the perspective of, while Amazon Batch can process jobs rapidly, it is a batch scheduler and will tend to optimize for cost, priority, and throughput rather than immediately running jobs. This implies that some queue time is desirable to allow Amazon Batch to make the right choice for compute. And so at HCC, there is no cost except for your time. But the caveat is that there's a fixed pool of resources on Crane and Swan, which means our batch scheduler that we run, which is Slurm, focuses on your job's priority with fair share and getting the most done based off of everyone's priority and the available resources. Where if a lot of jobs are taking up a lot of those available resources, then the queue time sits longer and longer. So it's kind of just putting it in a different perspective there as well. And this is the tricky question of how do you know how much to request? The short answer is we don't know. It really depends on what you're doing, how much data you have, the time of day, but not really that, but it really depends on a lot of factors. The long answer is it again depends on those factors, and the way that you can kind of figure it out more and more is figuring out, talking to a colleague who's maybe run some simulations, look at what the simulation uses on your local machine, and that gives you a very good idea. And so if you're translating from, say, your laptop or workstation to HCC, just requesting what your laptop or workstation is a fairly good start. And then, of course, trial and error with some job monitoring. And this is kind of also a fun example I love to use is just because you request a lot of cores doesn't mean that your job finishes sooner. And this is including a wait time and the actual time of execution, where this graph here shows the same analysis of COVID-19 spreading throughout the state of Nebraska, where all I did was just increase the number of CPU cores allocated to the job. And you can see that with, say, one core on the far left, it took, say, about 45 minutes. And as we go across to the right, where more and more cores are added, it speeds up as we would expect with kind of more of a step function. But as I was running this, the wait time for each job was getting significantly greater, to where it was actually faster for me to request less resources and have a shorter wait time, but a longer runtime. And so it actually balanced out to where I think it was about 8 cores had the least wait time, but still executed faster in total. So that is something to take into account. And so what we will actually do is our first exercise. So everyone should have their job examples folder ready to go. And let me go ahead and move this up here. Can everyone see my terminal on the bottom left hand at a good size? Give me a green check if it's a good size, red X if it needs to go bigger or smaller. Okay, so let me go ahead and clear my screen here. So I'm going to go into my job examples folder. And then I want everyone to go into one of the folders. I'm just going to go ahead and use the Python folder, for example. And there is a tool or a function of the sbatch command that we learned yesterday that allows you to kind of get an idea of how long it will sit in the job will sit in the queue based off of your submit script. And so what I'm going to do is I'm going to edit my submission file within this folder. And I'm going to change the parameters around it. I'd like you to tag along. You don't have to use the same amounts as me, but kind of play around with some different parameters. And then using this sbatch -- test only for your submit script, see how long it takes to wait. So if I do nano python.submit, and we can see here in my file, it's 1 core on 1 node with 5 GB of memory for 10 minutes on these first 4 lines. If I go ahead and run sbatch -- test only, python.submit, we can see that my job would start at, let's see, 3:18, which, so I guess it would pretty much start immediately, which it's a very small job, that's expected. And if I go ahead and edit it again, whoops, let me go ahead and just get rid of these 2 lines at the bottom because I don't know why I had GPU in there. But let's say I want to do a 50 core job with 250 gigabytes of memory for 10 minutes. And I write that file and I submit it again. By you having that larger resource request, we can see that Slurm estimates that this job would start no sooner than Saturday at 3:15, so nearly 48 hours later. So what I want everyone to do is kind of play around with that for, let's say, the next 2-3 minutes, and then post your observations into the chat. What did you notice as you adjusted different values? And something to note is that the -- test only has to immediately go after has to immediately go after the sbatch command. If it goes after anything else, it will actually submit the job, which will go against your priority and actually submit it to the cluster. So again, sbash -- test only, then everything else. But go ahead and play around with it and then post what you observe. You shouldn't need to install anything if you're running on Swan. So you should see this login.1 or login1.swan on the left-hand side. Were you is this the same terminal you may have used for the running software session? Yeah, so what you'll need to do is module load nano. And so we'll also go ahead and do this exercise for about 2-3 more minutes. And let me actually put a timer up, and then go ahead and post your experiences into chat, or use your mic and say what you've noticed. Okay, so some of the things you may have noticed is that as you increase the resources, at some point it probably got more than a minute or even more than instantaneous or a few seconds on your estimated start time. With Swan, the biggest limitation that we've noticed recently is the more you request on memory, the faster your job time or job wait time increases. While due to the higher availability of cores on Swan, you can fairly easily request a good amount of cores without too much issue on your wait time. And this is kind of where we're looking at helping researchers optimize, especially their memory requests, a lot more on Crane and Swan, is using some job monitoring tools that we have available, where for your workflows, after eventually you do some testing on making sure everything works, is you can check what resources are used. And I believe Mohammed briefly touched on this yesterday during his session, where you can use the saccount command to fairly quickly look at some of the different parameters that the job had when it ran. You can also use the job history command, and we recently installed a utility on both Crane and Swan called Ceph, not to be confused with the file system called Ceph, but SEFF, which is simply a Slurm efficiency, which is a brand new tool that is available on, and I personally prefer it as it's a lot easier to read. But to kind of compare these tools very briefly, and then we'll do some hands-on practice with these, is, let me actually make this bigger. This is what that saccount command will output typically, where this is a single job by a researcher, I won't say even yesterday, on Swan, where we can see how much memory they requested roughly. We can see how much they used somewhat. It's very cryptic, honestly, in terms of quickly looking at it. But you can see that they use about 14 gigabytes of memory in total based off of these two values in the middle. They requested, I'm not sure what their total memory is since it's listed in an acronym, but it ran for about 2 hours in total. So they might be able to reduce the amount of time they request since they requested an entire day. They might be able to request less memory depending on how they requested it overall. Overall, saccount is more designed, or at least more beneficial if you're looking at a large set of jobs. Next, for the same job that we have, for that same job, we have the job history command, which is a command we wrote in-house basically to make saccount a lot easier to read. So we can see for that same job, they requested 8 cores for a day with 64 gigabytes of memory. It waited for about 2 hours and 15 minutes, but ran for 2 hours in total and used 44 gigabytes of memory in total. So we didn't really see the full picture with saccount. And this is a lot easier to read. And this is a nice thing that we got out to try and help make resource requests a lot more efficient. And then there was a utility published by Slurm, which I personally prefer just because it provides a lot of insight into what actually happens. Where, again, for that same job that we saw, we can now see how many nodes they requested, how many cores per node, how much utilization of those cores was actually used, where a 99% efficiency is amazing for the number of cores, meaning they didn't request too many cores or didn't leave any unused. But this is where we can see that memory efficiency could probably be optimized a little bit more. Maybe they could request 48 gigabytes, just to be a little bit on the safe side, freeing up about 14 of those gigabytes for other researchers. And so they could modify their submit files, basically changing the 64 to say 48 or even 38. It depends entirely on their research as well. Maybe this was just a one-off case, but this is something that we're trying to help encourage, is looking back at previous jobs that you ran to help optimize your scripts, not only for giving more resources back to other researchers to do their jobs, but by reducing your own resource requests and optimizing a lot more, your wait times and your fair share are affected much less. So your jobs can start sooner and you can have more jobs run concurrently, which helps speed up your research, which is great. Everyone loves getting the research done faster. So we are going to do a little bit of an exercise here where we're going to go into our job examples folder again. So I'm going to just do cd work/job examples. We are going to go into the MATLAB folder within the job examples folder. And then I want everyone to go ahead and submit the serial.slurm script. Not with test only, but actually submit it. And what we're going to do is we are going to then look at these jobs with all three tools. And then after you have looked at your after you've looked at the job, after it's finished, using the three tools, kind of compare how you might modify the submission script to make the job request a little more efficient, and also post which tool and method you prefer and why into the chat. So I'm going to go ahead and submit my job here. And it's going to take about 90 seconds for the serial slurm for this particular job to run on Swan. So let's see, whoops. So if I do watch SQ, actually I'm not gonna go watch it. SQ grep. Yeah, I'm probably just gonna do an invert. So we can see a few folks have already started running the job. Let's go ahead and watch that here. So looks like all of our jobs are currently running. So we'll go ahead and let those finish. And I will actually quickly grab the three methods and post those into the chat for everyone, so that way you can directly refer to them. There we go. So I've posted the three methods into the chat box that you can use. You basically just replace a job number with the job ID itself, which on screen for me is 649585. Let me go ahead and make this bigger again. So let me go ahead and get a timer going again. Actually, we can ignore that. But yeah, so by default, while you look at what your jobs use, I believe they should be just about done now. The serial.slurm file, it uses one core, which is at n tasks per node equal to 1 times one node. and 10 gigabytes of memory per core. So 10 times 1 is 10. And then it has a time limit of 10 minutes. So once you've looked at the job with your the 3 tools I posted into chat, compare and contrast how those tools feel to you, and then also post how you might change the submission script. Could you post the command that you're trying to use the entire thing, or post the entire command that you tried in chat? If your job has not finished, it won't work. So let's go ahead and try that command. Huh. So it might be because some hidden characters when copy and pasting. So I just try typing it out. And this is kind of what another reason I like using Ceph personally is it's just 4 characters and a job ID. You don't have to worry about recommend, max RSS, time elapsed. When I do any kind of mass observation to basically kind of evaluate the performance of the cluster, I do use this account as it's easy to get a lot of data all at once. But for when I do jobs, I typically just use Ceph or job history just to quickly look. But what are some other things that you're noticing besides, I guess, prone to error that the saccount command is? Yeah, so we can decrease the gigabytes of memory. So what might be a good value to change it to? If we're aiming to about 50 to 70, maybe even 80% utilization of the memory. Yeah, so we could probably increase this to 3, 2.9 gigs. That might be a little close, but if it's consistently going to be 2.9, 3 would be perfect. So if I go ahead and grab my command here, and let me go ahead and run it. So we saw this account, it looks like in chat quite a bit. If we compare the command, the job I had above this, we can see 2.9 is probably fairly close. We might even want to push it to 3.5 as our change. So how does the job history or Ceph compare to using saccount? Or what are some things we're noticing? Or some thoughts? And feel free to mic up as well. Yeah, so Ceph does seem easier and has more info. It's also a lot, as you mentioned, as I mentioned, it's a lot nicer to read as well. It's also nice to be able to kind of see even CPU efficiency overall, where we can see that in this case, yeah, the large completed. Yeah, it's also nice to be able to see that our CPU wasn't used entirely, and that's probably just from loading MATLAB itself. But it's also a short job, so it's hard to really gauge how truthful that is. But if you are looking over a lot of jobs, saccount might be a smidge easier. There's some other open source tools. I think one's called like Report Ceph. That can basically be like a combination of Ceph and saccount. So if you're really wanting to go into it, there's options out there as well. To kind of get back on time, since we have about 20 minutes left. Let me go ahead and move my timer. So the big question that we often get is, how can I reduce my wait time? There's 3 different methods, or at least 3 different categories of it. There's the free version, which is submitting an acknowledgement request credit on your publications, articles, presentations, theses, and so many more, where basically once you submit that, you get a quality of service credit, which is currently only available on Crane. Eventually, we'll probably get it over to Swan, and that can be used to increase your job's priority. You can also just minimize the resource request to what is needed if you already know that. There's the free, which the only cost in this case is time, which is to split your workflow or job into multiple steps to minimize the amount of time and resources each step needs. So it's putting a lot of work in now to get benefit later. You can also make your jobs able to checkpoint or successfully restart if they're killed without issue, which allows you, especially on Crane right now, to run on what's called the guest partition, which is a preemptible partition that runs on leased hardware by other researchers. So while they're not using their hardware, you can use it, with the caveat that if they do need to use their partition, your job would get killed, which is why it needs to be able to checkpoint or be able to restart without issue. And then if your group has some money left, you can certainly pay to have dedicated hardware on our resources. That's the only one that's not free, or free with air quotes. We actually just opened up priority access or dedicated hardware on Swan. If one of the helpers could post the link to our priority access into the chat for me, that would be great. In terms of resource statistics on our resources, this was actually pulled last night, where on Swan, for jobs completed between September 1st and pretty much 7 o'clock last night, only about 12% of the memory requested was utilized on jobs requesting a gigabyte or more of memory, resulting in about 410 terabytes of memory just going unused. And then on Crane, this was only about 19%, so a smidge better, but about 1,300 rounding up terabytes of memory of 1,600 went unused. And so this is a problem we're trying to help solve, is getting more utilization of our clusters, to where if these were, say, reduced to where 50 to even 90% of the memory was utilized, or the requests were reduced to make it so, more researchers, including those adjusting their own submission scripts, would see the benefit of their job starting sooner and being able to do more at once. Where if I pull up Swan here and use Slurm to do sinfo, basically Slurm info -o, and just get the status of the cores. This basically shows the allocated cores, the idle cores, and the total cores available on Swan to use by worker nodes. Where right now we have 5,000 idle cores on Swan just wanting to be used. And so this is something else we're trying to help improve through this workshop session, is ideally shift the transition to where we're limited by CPUs or closer to that. Any questions about optimization so far, or at least request optimization? That was kind of a long run. Feel free to type it out in chat, and if you do type it out in chat, please give me a green check mark or a red X. Otherwise, mic up. I don't hear anyone. I don't see any indication of typing through reaction. So we'll go ahead and move on to data safety. So as with the general files, keep multiple copies of your data is kind of the big summary of this next talk, where, as some context again, we have 4 different file systems at HCC. And going from left to right, we have attic, home, common, and work. Where as we go from left to right, the redundancy or numbers of copies on the file system itself goes down to where attic, we could lose the entire city of Omaha or the entire UNO campus or the entire UNO campus, and there'd still be a copy of the data on attic either in Lincoln or Omaha. Home, it's backed up daily, but it's also very small. Common, there's no backups. And then work actually not only has no backups, but has a purge policy where if a file sits basically untouched or unutilized for 6 months, it goes into the void and gets deleted. That has caught quite a few researchers in the past as well. Attic is our nearline archival service that we offer at the time of this session, $28 per terabyte per year to research groups, and is intended as a nearline archive service that is not mounted on the clusters. It is available through Globus, which was talked about earlier or yesterday as a way to transfer files kind of just in the background at a high speed. And then we kind of just talked about that. And so how to keep our data safe, multiple copies of it is the straight answer. And I like this little comic of the 4 stages of data loss, where there's just a poor grad student who accidentally deleted their data with rm-rf, or at least that's what I assume they did. And they lost quite a bit, it seems. So the common question or common statement that we sometimes hear is, it couldn't happen to me. I keep good care of my files. These are some actual examples that we've had in recent history on our system, to where we've had multiple months of work or multiple terabytes of data just lost primarily due to the purge policy. And this purge policy is in effect not because we want to be mean. It's because if we didn't purge files every once in a while through that 6-month policy, which happens automatically, we don't do it manually ourselves, the file systems would just fill up very quickly and would become rather slow. And the work file system especially is meant to be a very hot, fast, temporary storage space for your files, rather than somewhere to permanently store your data. And so we've had 22 terabytes lost, which was 12 months of their research. We've had a graduate student's entire set of notebooks, code, and data loss for their thesis. We've had someone even accidentally rm-r their own work directory. So it's important to be careful of what you do, but also to keep multiple copies of your data and not store it solely on the work file system. Some general ideas is keep multiple copies of it, ideally with some in multiple locations, such as the 3-2-1 backup rule, where you have 3 copies of your data in 2 different locations, with 1 offsite, which is the more traditional term for it. In reality, if you have, say, 1 copy on, say, Crane and then 1 copy in OneDrive, that OneDrive is technically your offsite location. For your scripts and notebooks, use something like Git in a remote repository, such as GitHub, GitLab, or the university's GitLab instance for your scripts. And make sure to back up your data in repository frequently. The more often you do it, the less data you'll lose. And make sure to double check your backups and your pushes to make sure that they're actually working. Some possible locations that are available to you is the university OneDrive. Your laptop or workstation works as a good temporary measure. HCC's Attic service or other cloud providers such as Amazon's S3, the Google Cloud Platform, B2, Box, Dropbox, you name it. There's a lot of them out there. You could even potentially have one in your lab. Some advantages of disadvantages of these general 4 categories is that the University OneDrive is a common good service provided by the university, which in lay speak just means it's free for you to use and is just provided by the university as a whole, where there's unlimited, and I'm going to put an air quote in that, storage available for you to use. It's fairly easy to share it with your collaborators. And currently only for the UNL OneDrive, it's connected through Globus, which makes file transfers a lot easier. The downside is that it can be a little bit slower to upload files to. I've seen mostly 10 megabytes per second, which for some things is fine, but if you're doing multiple terabytes all at once, it can be fairly slow. Oftentimes it's sharing only within the NU system, and oftentimes, unless you're using Globus, will require a desktop app or the web interface. Going on the other side, we have your laptop or workstation, which has pretty much the only advantage of it being simple and familiar to use, but it relies entirely on your internet speed or your network speed on campus. It's limited in how much it can store. It can be damaged or stolen. You're managing it entirely, and you can't easily share your data from it if you need to share it with a collaborator. HCC's Attic is connected to our high-speed networking, which means that basically if you're copying from Crane or Swan to Attic, it's going to be as fast as it possibly can go, especially since they're pretty much in the same room as each other. So there's going to be no limit there. Sharing can be done through the Globus web interface, which means it's easy to easier to share with external collaborators as well, especially compared to OneDrive. And the storage is entirely managed by HCC staff, though you would still have to set up the backup process yourself. The disadvantage to it, though, is that it does cost money at $28 per terabyte per year. Automation is only available through Globus or your own scripts. And to directly access Attic, you'd need to have an HCC account or set up a Globus share to do that. And then for other cloud providers, it really depends on the provider itself. But some of the advantages is that they use common protocols out there that can be used with many tools to back up your data. And a lot of the advantages depend on the provider itself. The disadvantages is that typically they're not free. And some of these providers have fees where it's free to put it up in their cloud, but they charge you to take it out of their cloud somewhere else. Attic does not do that. We just charge for the storage. The other disadvantage is that you're doing a lot of the support yourself, and a lot of them can only be accessed through a web browser or CLI or command line interface. And there's different ways that you can use these different areas where typically Globus can interact with all of the methods. For a lot of the external or the other cloud providers area, Globus is a little bit hit or miss unless something is already set up. OneDrive is also only available for UNL students, staff, and faculty at this time. There's a tool called rclone, which we have listed out on our documentation, which works great with many different cloud services and can work with your workstation, our Attic, OneDrive from anywhere, including your own personal or lab OneDrive, and other providers. You can certainly manually copy and paste things around or manually use the command line for all of them. You can use rsync or SCP to copy to and from your workstation or Attic. And then many of the other surfaces have their own different protocols that you can use, like say S3. And then before we go to the final thing, are there any questions about that? If you're typing, please give me some kind of reaction on Zoom. But otherwise, feel free to mic up. All right, I don't see anything in chat and I don't see any reactions, so I'll go ahead and get to our last thing. And then finally, basically kind of how to get a little bit more efficient support. So research is all about collaboration, including between us and researchers as HCC staff. And so particularly when you ask us for support, even when asking a colleague for support, it's beneficial to include as much information as possible about your issue or about a problem or you're trying to solve. And so in our case, if you email us or talk to us directly, it's some kind of examples of important information to include about your issue or problem is a way to help reproduce your problem so we can do a lot of testing on ourselves. The software involved in it, any troubleshooting you've already done, that's always great to help, as it kind of gives us an idea of how your software is being used or where there might be an issue in the workflow. Error messages are always great, as well as the job IDs and scripts you're using, your HCC username and resource being used, any output or error files. And this kind of just goes to the whole, the more you can give us, the more we can help you. But a similar thing goes to asking your colleagues or your lab partners as well, as they might be able to say, oh yeah, I had that error back when I was starting out or back last week, and this is how I solved it, because it might sound more familiar to them with more information. And then kind of just a big summary of today's session, since we're running short on time, is being a digital assistant on HCC. Request roughly about only what you need for your job to finish, including time, CPUs, and memory. When you're done with a project, compress or archive the projects when you're done with them, as this not only saves on space in your file quota, it helps keep the file systems performant. And when you compress and archive them, it makes them a lot easier to move around for your backups. Regularly backup your scripts and code. We just finished talking about that. The University of OneDrive is a great place to get started with, and there's other solutions that work very well. Just again, be aware of the purge policy. If a file sits around for 6 months, it goes away, and there's no way for us to get them back, as they're just deleted. There's no recycling can, no trash bin. They're just unfortunately gone. And then don't run workflows on the login nodes. It's fine to do a quick little 5-second test of something just to make sure if something executes for a few seconds. But if you really want to do something interactively for testing, use the interactive job that we talked about earlier. And then that's it for the session. Are there any questions at all? Oh, and I should post our support email and our documentation link.